Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. This AP Chemistry video is about writing molecular and net ionic equations for weak acid and strong base reactions. It's worthwhile going to my website, Miss Muskeluk AP Chemistry, and checking out the AP14.15 Net Ionic Reactions and Strong Acids before you view this video. Well, let's go here. Let's assume you've watched those other two. We've got a reaction where we have stoichiometric amounts of hydrofluoric acid and sodium hydroxide being mixed. Well, you're pretty well acquainted with sodium hydroxide as being a strong base. Hydrofluoric acid, though, is something that's a little bit different. Hydrofluoric acid is not one of the strong acids. Here you can see the list of the 6 strong acids that you should know in AP, and hydrofluoric acid is considered a weak acid. And what makes it weak is that as a molecule, HF, when it's in solution, immediately making H plus ions and the respective anion 100%, so that there's none of the original molecules. The HF doesn't ionize much. It's less than 4%. Imagine this size reduced down to 4% to the original, and you'll see how much of the acid actually ionizes with water. As a result, when we write hydrofluoric acid in a solution, we really shouldn't write it as being separate ions. We should write it as being molecular. Something else you should know about hydrofluoric acid: it is a very, very dangerous substance. The warnings on it are a multitude. Before you work with this in any shape or form, you should get some safety training. You should have the antidote, so you should end up having all the protective clothing. You want none of this on your skin. It causes severe burns, which may not be painful, but can be fatal. So this is something you don't want to mess with. If you are required to work with hydrofluoric acid, make sure they provide the protective clothing and instructions and have the antidotes. Otherwise, quit. So let's go back to our reaction and find out how we can deal with this, doing a balanced molecular equation. Well, just as any other acid-base metathesis reaction, we just switch things around. In the case of an acid base, we're going to make water. So you can just say, hey, water is being made. That's going to be your first product, acid, base. And our base in AP chemistry is almost always hydroxide. So there you go. These are aqueous, and the sodium hydroxide, of course, is a soluble base. Now, what else is produced? Well, we simply switch the sodium and the fluoride. So you can write the second part here of our reaction, sodium fluoride, which is aqueous, and we've got our molecular equation. Everything's balanced: 2 hydrogens, 1 oxygen, sodium, and a fluoride. Here we've got our fluoride and our sodium. They're both plus and minus 1. Interesting. Hydrogen fluoride is the only halogen acid that is not strong, and it's tough to explain why. There's a lot of factors involved, and we'll deal with that when we talk about the strength of acids. Well, this is nothing new. We've pretty much done this as we normally would, nothing different than a strong acid or even an ionic reaction. We just switch ions around. The net ionic reaction, though, is a very tricky one, and this one is used quite often. You'll find that weak acid net ionic reactions are a common question on the AP exam. Now, we'll start off with saying that we have hydrogen fluoride, but remember, I said this is a weak acid, and all of the weak acids, and there are a myriad of them. And you've got acetic, you've got folic, you've got stearic, you've got deoxyribonucleic. All these acids, they are weak acids, and they don't break up that much. So if we're going to write them as being in a solution, we would have to say that they are as a molecule. The hydrogen predominantly is always attached to its anion, that they're stuck together as a molecule. And it's actually a covalent bond. This is a pretty accurate representation. Now, the sodium hydroxide, that's an ionic compound, and that is going to be sodium ions and hydroxide ions. We know sodiums are all soluble. These are our reactants. Notice we've got 3 reactants, not 4. With a strong acid, we'd have H plus and fluoride minus, because the strong acids all react with water to make ions. They ionize. But weak acids are not good ionizers. So we're going to make our product. Now we still have our water. That's nothing new about that. That is one of our products. Our other product that we have is still sodium ions. They don't do anything. That's our spectator. They've always been a spectator. They're excellent spectators. Give them a ticket and they'll watch this reaction occurring. Now, what else do we end up having? Now, we've taken the water, we've taken the sodium, and we've taken the hydrogen, so what's left behind is the fluoride ion. The hydrogen jumped over to the hydroxide and left the fluoride hanging here. It's its ion. Notice that we have a +1 and a -1. We still have a neutral side, and we still have a neutral side. We have conservation of charge. This is the entire ionic equation. We've shown all the ions and all the substances. But notice, the sodium doesn't change. So if we want the net ionic equation, we wouldn't include the sodium. That's a spectator. We still keep our HF. And this is what's different. On a strong acid, we don't have this together. We've got it already ionized. But the HF reacts, so we have to say, hey, this stuff's reacting. It's not a spectator. And it's an aqueous solution. You don't have to write aqueous on an AP exam. I did it here just for clarity. And we don't include our sodium because the sodium didn't change, but what did change is the hydroxide. The hydroxide turned into the water, and the HF turned into the water, the H part of it. So these are our two reactants that are reacting. In a weak acid reaction, instead of having H plus and OH minus, you have the original molecular form of the equation. That's the difference. And this is the stuff that we've got a certain concentration of. It's going to react and make, of course, water, our liquid. The hydroxides are accounted for. The hydrogen is accounted for, these two hydrogens. So we've got two. But we've got this fluoride, which has been orphaned, and we have to include it. Now, one extra thing to note to make sure that you've done this right, let's add the charges up of the products. Well, one fluoride. -1. Now, we're going to have a -1 on the reactant side. And here, we do. We've got it. This has a conservation of mass, has a conservation of charge. Everything is balanced. The substance that has reacted is shown, hydrogen and hydroxide. And the substances that have changed here, other substance that changed here, the fluoride is included also. And it's in aqueous solution. 3 methods of showing what's happening. The, I think, most exact one is the full ionic equation because it keeps track of all the ions and molecular substances. The molecular equation is pretty complicated too, but it really doesn't tell you about what's ionized. Here, the net is, this is the stuff that's really reacting. So if you're interested in the reaction itself and not worried about spectators, this is the simplest way of showing it. Here's our net ionic equation for a weak acid, and this could be any weak acid. As I say, this could be the acetic acid, it could be propionic acid, any one of those acids. That's how it's different from the strong acids, which are just H plus and OH minus. All right, we now have done 3 parts of this 3-part molecular and ionic equation series.